Yeah. So, good afternoon, all. Welcome to this third session of this day four of this FDP. So, now we have someone from IIT Tirupati, Dr. V. Vignesh, who is an assistant professor in Department of Electrical Engineering, and his research interests are in cyber physical modeling of smart grids, electric vehicle integration, grid impact of electric vehicles and storage, transactive energy, and cyber physical analytics for smart grids. He's also working on applications of artificial intelligence and machine learning in automated fault diagnosis in power grids. And to tell about Dr. Vignesh, he obtained his PhD in 2016 from IIT Kanpur in India, and he was a postdoctoral fellow at Smart Grid Demonstration and Research Investigation Lab at Washington State University, Pullman, USA. Currently, he is working as assistant professor in IIT Tirupati since 2018, and he has published a lot of research papers, especially in part IEEE transactions, and he was also awarded POSOCO Award for the best PhD thesis all over India in the year 2016. And Dr. Vignesh, thank you for accepting our invitation and agreeing to give this talk. So now I request you to deliver your talk, Dr. Vignesh.
Thank you, Dr. Narayanan, for the introduction. It's really my pleasure to be a speaker during this session. So my association with Shastra is it's like multidimensional because I belong to the same city. I stay very close to the University of Shastra. And then I know Dr. Narayanan from Kanpur days when he visited for a faculty development program, a workshop in RDDS way back in 2015, I guess. And then I again met him in one of the conferences in US. In fact, my own brother, he had graduated from this university. I know this university very well, and in fact, I love the campus. So it's my pleasure to be a speaker for this session today. And again, I would like to thank the Sastra Management, Department of Electrical Engineering, and of course Dr. Narayanan for calling me as a speaker. All right, so I'll just quickly start sharing my screen. So in the interest of the bandwidth, I would like to turn my video off, but whenever there's a question or when there's interaction required, I would like to switch it on again. So I guess this should be okay. So let me share my screen. Oh, just a minute. Looks like I have to allow the settings to let me share the screen. So just give me a moment. Narayanan, just a minute. I'm just the Google the application is not letting me to share the screen again. Let me
No
just
problem.
fix it quickly. I'll
No
just
problem.
fix
You
it
take your time and fix it. Right.
Yeah. So. All right. I'll try now. I'll try. I'll log out and log in for a moment so that I'll just see if it's fixed. Just bear me for a few minutes. I'm sorry about
Okay,
that.
Vignesh. Yeah,
Yeah.
fine. We'll wait. We'll wait.
Yeah.
Yeah, just a couple of minutes because I think there is some internet connectivity issue at his end. Just a couple of minutes for him to log in back.
Narayan, I have emailed my presentation to the email ID. Could you open it and share it for me, please?
One second.
Yeah. It's for that FDP
Yeah,
email ID.
yeah, official mail ID, right?
Yeah. AT pattern.
Mail
So let
now?
me.
Did you mail it now?
I've just emailed. I've just emailed. You should have got it by now, I guess. Some setting is not letting me to share the screen. I'm not able to fix it from the side. I'll just.
One second, one second. Because I haven't received that email.
1 minute.
Are you very sure that you have sent it to this official ID?
Yeah, SGDCO
Yeah,
at.
yeah. Fine, 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 fine. It should be coming.
Let me know. Otherwise, I'll share you in a Google Drive.
One second, one second.
A little big file, so that's why it could take a while to. Sometimes this Mac creates this problem.
No, Vignesh, we haven't received anything.
You not got it? Okay, I'll share it in Google Drive. Give me a moment.
Yeah, 1 second, it has come. 1 second.
That's come?
Yeah.
Yeah.
1 second.
Let me know if you have received it. Otherwise, I'll resend
Yeah,
it.
no. We have received it. Just downloading and trying to share it. Is the screen visible, Vignesh?
1 minute. Let me check.
We have shared.
No, it's still not visible to me.
No, we are presenting it actually.
1 minute.
So participants is
Yeah,
like this.
yeah,
Is the screen visible to the participants also?
yeah.
Anyone?
But I'm hearing getting an echo.
Yeah, Vignesh, it's visible for us
Yeah,
and the
yeah,
participants also.
yeah. It's just visible for me. Just give me a
Fine.
moment.
So just let us know what is to be done when you want to change the slides. You just let us know.
Yeah, sure. Yeah, okay. Could you please go to the first slide? Yeah. Okay. Thank you. Sorry about this delay on this. Um, so as I said, I would be today talking about some of the modeling and control aspects of smart grid, which is cyber physical in nature. I'm sure for the last couple of days, you might have listened to senior experts who must have exposed you to what is a smart grid is. So I might touch a little bit on a brief introduction, and then I'll come into the modeling and control aspects of the smart grid. That's the whole idea. So I would like to thank IIT Kanpur and Washington University and Siemens USA, Vanderbilt University USA from the collaborative work that I'm going to present here as part of it. So as I said, this is going to be a lecture, not exactly a lecture, I would say. It's going to be some of my experiences in working with smart grid and its challenges that we faced when we developed models for smart grids. So I'm relatively a new researcher in this area, so I would appreciate if you could give us your inputs on it. Thank you, and could you please go to the next slide? Yeah. So I'll just introduce what is a smart grid exactly, and I'll not take too much time on it. And then I'll talk about a little bit on power system load modeling, because modeling loads is one of the most important aspects when it comes to the overall power system modeling. Then I will be talking on wide area damping controllers, a step ahead, in which we get the data and develop the controllers and test it in real time. And going a further step ahead, I would talk about the cyber physical nature of the smart grid and why we need to model the cyber and physical aspects of the smart grid together. And then if time permits, I guess I will touch a little bit on the transactive energy and how do we detect cyber attacks. What is the effect of the cyber attacks on a smart grid in the first place, and then how do we detect them? So this is going to be the overall purview of this lecture. Yeah, next slide, please. So you must have all known that electric power grid is one of the most complex man-made systems, right? It is an amazing and awesome interconnection of various apparatuses which make the entire grid. And we see this as a generation portfolio, a transmission portfolio, and a distribution portfolio. So all this put together is going to make our grid, which is running today. Next slide, please. Yeah. So the way the conventional grid that is operating today is, most part of our grid is like you have a generation portfolio wherein you have the various types of generation, and you have the transmission portfolio, and of course you step up the power you generated to transmit. We transmit at a higher voltage because to save the losses, and then we step it down as we consume it. So everything is kind of interconnected, and you of course you have some control centers to monitor the entire operation of the power system. Yeah, next slide, please. Okay, so you have energy control centers across the country. So you have you have one national level load dispatch center, national control center, New Delhi, and of course you have it for each region. And we have this SCADA system right now, which is kind of more in practice. We all know what is SCADA, supervisory control and acquisition system. And it is kind of the brain for the the heart and brain for the entire power network. And of course we have an energy management software that is running on the control center, which tries to come up with some important algorithms that we run based on the data that we receive, like let it be a state estimation or a wide area damping control application or an optimal power flow, whatever it is. So this is how this is the job of the control center, of course. So we will see how these control centers can be configured, in what are the different ways to configure the control centers later in this lecture. Now let's assume that it's only one master control center that kind of monitors and issues control actions based on data that it receives. Next slide, please. So this is I took some of these photos. You can see all these components in a typical in a typical SCADA based arrangement. We have the remote terminal units. You of course you have the substation that is shown at the top, and then you have the remote terminal units, and then you have a master station that is connected with the communication link, and then the data is being communicated to a control center which has the EMS running on it, so that people can see what is happening on various transmission lines, what is the power flow that's flowing on various transmission lines, and what is generation. Everything can be kind of looked on the screen at the control center. And if there is something that needs to be done, some control action needs to be done, the control center issues control command back to the control to the substation through the same communication link. For example, if you have to open a breaker, it issues a command, and that command is communicated to the substation back again. So this is kind of a closed loop operation. So we sense, we do some algorithms, and we issue some control command back, and then we see what is the effect. So it's completely a closed loop system, even now with the SCADA. But SCADA has its own disadvantages. I know you must be knowing about it, and people must have also talked about it. It has the refreshing rate is relatively slow for the SCADA, typically in 2 to 5 minutes. The next slide, please. Yeah, some more pictures of the control centers that I have visited. This one is from one in US. The last one that I showed one was from India. Yeah, next slide. So the power system is one system that is kind of very dynamic. Things keep changing in the power system. Sometimes the changes could be positive, and sometimes you can have unexpected faults in the power system. For example, in this case, there is a lightning strike, which could affect your transmission towers and the transmission lines. Next slide, please. Yeah, and we can also have weather related events like lightning, wind and snow. Maybe if there is a flood, or if there is a heavy snowfall. Snowfall is not very common in our part of the country, southern part of the country, but it could be a snow or a storm or anything that can cause breakdown of a component in the power system. That could be disturbance itself. And yeah, you can ask questions if you have anything. You can interrupt me, or free to interrupt me. So let's not have it as a monologue. If you have any questions, you can just ask it right away. Okay, next slide, please. Sometimes the breakdown could be because of the insulation failure, the worn out devices that typically happens in, say, for transformer. It could fail because of some insulation failure and all. So this is something that is an operational issue. So you can categorize these disturbances as natural disturbance and operational disturbance. And we are going to talk about another type of disturbance that is man-made. If everything else is normal, the human can interfere with the operation through coordinated attacks, and that attack can itself cause a very deteriorating effect on the power system. So that's something that we will look on. So that's not listed here. Let's go to the next slide. And this could be as trivial as this. An animal can, typically, of course, in some countries, trees and animals, can cause faults by such a scenario. So this is again not in our hands; it's out of our control. So this power system is kind of a dynamic system. The load can keep changing, or it can have inherent disturbances, as I have listed now. It can have cyber attacks. It can have a natural weather-induced event. Anything can happen. So as a power engineer, our goal is to make the system resilient to such disturbances. Perhaps I would define what is a resilience and what is the right context in which we should use the word resilient later. As a power engineer, we have to make the grid self-healing to such disturbances, right? So we cannot completely get away with these disturbances. So we have to build our grid in such a way that it can withstand such disturbances. And ultimately, the goal of any power engineer or any power system is to have a reliable and continuous power supply to its consumers. Yeah, that's the aim. Next slide, please. So suppose we don't do that. What can happen is, the worst thing that could ever happen is to have blackouts, and the globe, the world has seen some major blackouts, in the past, and most of them have caused so much of economic loss to the countries wherein the blackouts had occurred. Next slide, please. Yeah, so this is a list of blackouts that happened in the past, and the duration of the blackout, and the population that it had affected. If you could see the last one in about 10 years back, a major blackout occurred in India. wherein we lost around 48 gigawatts of power, and it lasted for a few hours. It had actually occurred on 30th and 31st of July. That is the time wherein there was summer peak, and it was a cascaded kind of a failure. That's what the report says. And we lost around 48 gigawatts of power for a few hours. So we have also seen a blackout in our own country. So what is the solution? That is what is going to come up next. Next slide, please. So there are some of the challenges in the power grid as we have seen now. Some of the challenges have been existing, and some of the challenges are relatively new. For example, the most recent challenges is the cyber vulnerability, because the cyber physical smart grid can have cyber vulnerabilities. Someone can intrude into our grid and they can disturb the grid operation. This in fact has occurred in Ukraine, and there was some of these attacks. I mean, there were talks of attacks that happened probably in Mumbai, but it was not shown in a great detail. But anyway, the Ukraine attack, which occurred back in 2015, was a very major disturbance in the Ukraine power grid, and that occurred because of a cyber attack. And we will see how that attack had occurred, and then we see how that could be simulated in our lab environment. And now we have increased penetration of microgrids and distributed energy resources. This is a challenge because it affects the operation of the grid in multiple ways. One is like the microgrids predominantly have renewable sources of energy like wind and solar, which is interfaced to the grid using some power electronic converters, right? And such interfaces lack inertia by themselves. So the conventional grid has rotating inertia coming from the generators. So the frequency stability was not a great problem. But with the less inertia because of the high penetration of microgrids, the inertia is a problem now. And people have been working in this area, but creating virtual inertia through special control techniques is one area in which is giving rise to many research opportunities. And of course, now we have very stringent economic and environmental constraints. So at one side, we say that the renewable energy is good for the country because it is kind of environmental friendly, it has carbon neutrality, things like that. But on the other side, when you come actually into practice, you see that going for 100% renewable is also a problem because of this inertia. Inertia is just one example that I gave you. There could be other issues like designing a proper protection systems and all. I'm sure people would have talked about it in their lectures. And now customers have very high reliability expectations from the power grid. Yeah, next slide, please. So the future power grid, it is not anymore future. We have already started coming into the era of smart grids. So the smart grid is a very the Department of Energy defines this as a class of technology people are using to bring utility delivery systems to the 21st century, which will have increased automation, and it will have remote-based control. It will have minimal human intervention. It will have a two-way communication and things like that. So this is a new era for the power systems, I would say. So this smart grid actually tries to keep the grid self-resilient and self-healing. Yeah, the next slide, please. Okay, so smart grid is not a single technology. It's kind of an happy marriage between various technologies. Like you name a technology, you can find in smart grid. Let it be sensor technology, or let it be a communication technology, or let it be things like smart meters. There are various technologies that are coming up, and we are in fact imbibing those technologies to make our grid more and more smarter. So some of them have been already in practice. For example, in the case of sensing, PMU and high rate fault recorders have already been installed in some of the power utilities and important substations that give you a better insight into your grid. Right. So next slide, please. So if you ask me what is a smart grid, this is one favorite cartoon what my advisor had taught me when I was taking a course on smart grid. Smart grid is actually, if you look at it from various angles, it would look different. Like for some people, if you ask what is a smart grid, they would say like increase consumer participation. Someone would say it is an increased penetration of renewables. Someone says it is a self-healing. It should have self-healing capabilities. Someone would say it has high resiliency. So it's like looking at a elephant and coming out with some various conclusions based on the angle at which you see the animal. So smart grid is in fact not just one thing. It's all about the various aspects that I just spoke about. It has to be looked from a broader perspective. That's my whole idea of putting this cartoon here. Next slide. So smart grid now has various components, and in itself, right from the generation aspect till the consumer side, it has its own kind of verticals and horizontals. And one major aspect that we would be seeing today is the demand side management, a kind of demand side management which we are going to call it as transactive energy if time permits, and we are going to see distributed control. You see, in the current grid, there's only one master control center which kinds of controls the entire thing. The question arises: what would happen to the grid if the master control system fails? Uh, to answer that question, we are kind of decentralizing the entire power grid to make it more resilient and make it more reliable. Reliability, resiliency are two different terms. I'll talk about them later. So, so those are two aspects that we would be addressing today in this lecture. Yeah, next slide, please. So the smart grid has various capabilities and characteristics. We expect a smart grid to be having an increased use of digital information and communication control architectures. It should be sustainable. It should be self-healing. It should be able to have an increased consumer participation. It should kind of have more and more. It should adapt to more and more new types of loads, such as electric vehicles. Now, on the load side, we have started having electric vehicles. They are going to dominate, uh, due to the carbon neutrality goals of various nations. Electric vehicles are going to come into the system, and of course, it's going to have its own effects on the grid. So these are various attributes of the smart grid, and if you ask me, as your title rightly says, I really like the title of the program, drivers and challenges. Some of the we are going to see some of the driving technologies now. We are going to see what drives the smart grid technology. Could you please go to the next slide? Yeah. So enabling technologies, I've just put a few in, few of them. There could be many. Communication technologies, IT, demand side management, automatic metering, microgrids, home area networks, distributed automation, new types of sensing devices like PMU. So all of them are going to drive this to smart grid technologies, and we are going to touch a little bit on few of these aspects today in this lecture, and we see what challenges and what positive effects they have on the grid operation itself. So let's go on to the next slide. Okay, so if smart grid is actually a kind of a very beautifully layered structure by in itself, right? Like if you ask me what should be the layers that are going to come, I'm sure you must have seen this way of layering out. It's going to have a component layer which is going to have all your physical systems. For example, generation, transmission, distributions, and in fact, on one plane is going to have various zones. Like for example, process zone, field zone, station zone, market zone, and things like that. And over the hardware layer we are going to have a communication layer, which is communication information layer, of course. So which is on the top of the physical layer of the smart grid, and there is a functional layer. The function layer is going to run some of the analytics from the information and communication layer. So we are going to address two of one typical application, for example, is the remedial action scheme that's going to happen. Yeah, I think Narayan, we lost the. I'm not able to see the. Yeah. Thank you. And on the most top part of it is the business layer. Is going to have business objectives, policies, and regulations. So we are not going to touch on that again. So we'll restrict ourselves up to the function layer of the smart grid, and all these areas should have an interoperability dimension. That's the main goal. Yeah, let's go to the next slide. So the conceptual model is that it's going to have the way it is conceptualized is like it is going to have. Oh, I think I lost screen sharing.
Sir, kindly wait, sir.
Yeah, no problem.
Yes, sir. Please continue, sir.
Yeah, okay. So it's going to have a completely interwoven communication and IT infrastructure. That's the takeaway from the slide. So I'm not going to go into more details in the interest of time. Let's go to the next slide. So okay, I think I know why this is getting repeated. Could you go to the next slide, please? Next slide. Yeah, okay. So the way we are going to kind of analyze this smart grid is we are going to predict, plan, and operate. There are three aspects of this. We are going to mainly restrict ourselves to the operational aspects of the smart grid, and situational awareness and decision support are something that is very interesting research area that people can think about. I'll just touch on it towards the end of the presentation. So to enable a smart grid, we need to have all these aspects. I'm going to mainly focus on the operational aspects of it, like how to sense, communicate, compute, and control. So I'm going to take one typical example of each, and I'm going to tell you how things are done and what enables these technologies. Next slide, please. So if you see here, this is as I said before, the whole operation of a smart grid is a closed loop system. We kind of have some of the inputs to it. Like for example, we take the observed response and we have a measurement based information system, and we give it to a decision process layer, and then we have an automatic control, and we have system operation planning coming from the decision process, and most importantly we are going to have this disturbances coming on it. So the goal of the smart grid is to make this power system more and more resilient to these disturbances. And as I said, these disturbances could be man-made, or these could be natural, or this could be weather related disturbances, or this could be even operational disturbances like insulation failure or something like that. So the whole structure has to ensure that the power system is kind of resilient to such major disturbances, and we ensure reliable power supply to the consumer. So what that would mean is, if you have better information, that is going to give us better decisions, right? So if you have more information, you could make out most of the information to come up with a proper decision and proper algorithms to make your grid more and more smarter. Next slide, please. So if you see how this data grows into how we visualize this is little interesting. So we have the data, that is the raw data that you get from your smart meters, PMUs, and whatever it is, and you derive information and data are not the same thing. They're two different aspects. And we take the useful information. From the useful information we get the knowledge, and from the knowledge we go to the wisdom. So it's more and more tapering towards the top. So what operator needs is the information and of course the wisdom. So he definitely not just the data. So the problem is, one of the major challenges is that we have now lots of data coming in, and people are not very sure about what to do with the data, and how do we use the data to best of the in the best interest of the smart grid. So that's one major challenge. So so I will touch on your FDP title there and there. The data cannot just operate your smart grid. The data has to give you some useful information which the operator can comprehend, and he can make some sensible decisions from the data that he is getting. So just having files of data is not of any use. That's what is emphasized in this slide. Next slide, please. And yeah, so to better sense it, we need to have better sensing technologies, and the current grid has PTs and CTs, IEDs. Now the most recent development is the phase measurement units. People have worked on where to place the PMUs, what are the optimal locations of the PMUs, on what basis should we place the PMUs, because PMUs are not very inexpensive devices. They are very expensive. So we need to place them very judiciously. And now we have smart meters, we have fault indicators, fault recorders. Everything comes into this umbrella of sensing technologies. So out of which PMU is something that is going to, which is playing already a major role in sensing. So I'll talk mostly on the applications of the PMU data. Next slide, please. So why do we have to go for PMU? What is wrong with existing SCADA and analog technologies? If you ask me, there are kind of lots of noise in analog based technologies. There is no way to filter them. And other important disadvantage is that it gives you just the RMS value and not the phasor value. So can anyone say what is the difference between getting just the RMS value and the phasor value? What is the major difference? Can anyone say? So what is the problem in just getting the RMS value and not the phasor value? Can anyone come out with an answer? So the SCADA gives you only the RMS value, and to get the phasor value, we need to go for state estimation. Even in the state estimation, we don't get the exact phasor values. We get the phasor with respect to a reference. We take one system as the slack bus, and we refer the phase angles of other quantities with respect to this slack bus. So just having the RMS value and not having the phase angle information is also a disadvantage. So for example, and it has and above all, the analog sensors have the limited flexibility compared to the digital counterpart. one typical example is that it has positive sequence data. So you can get positive sequence data directly from the PMU values. Yes. Next slide, please. So one popular, saying is that going from SCADA to PMU is like going from an X-ray to MRI of the grid, right? So SCADA is just like an X-ray, and whereas PMU data is going to give you, it's like as you can compare the PMU to an MRI of the human body. So this is one popular saying that Terry Boston had just told. So C37.118.1 defines the PMU protocol mostly. So so PMU is a device that provides you current phases, voltage phases, frequency measurements, rate of change of frequency for three-phase AC voltage and current waveform. So it converts the analog value to phasor. That's to put it in a very raw definition. It takes analog values from the CTPTs and gives you the phasor with reference to an absolute reference. It's not a relative reference, to an absolute reference, which is obtained from the GPS clock. Next slide, please. So the way it is being structured is like, for example, you have PMUs, various PMUs at the PMU stations. So multiple PMUs report to the PDC. PDC means phasor data concentrator, wherein you have the data filtering, data time synchronization, time alignment, everything happening at the PDC level. And of course, PDC can also do some of the applications by itself. It has some intelligence to do the application, and the PDC report to the local operational or regional operation. From the regional operation, it goes to the national operation, which is more and more wider. So that's what we're going to talk about, wide area systems. We are going to talk about wide area damping controllers. So how from PMU data can we make a control decision is what going to come up next, I think, in the presentation. Next slide, please. So PMU gives us voltage, current, frequency information that goes to the PDC. From the PDC, we also have the SCADA value and other displays. And we have the system controls, which makes the real-time control decisions like voltage stability, reactive power support, center area angles, limits on the transmission lines, and things like that. So when you have both PMU and SCADA data, you would have a kind of a hybrid system. But only with the PMU data, the advantage is that it has a very high refresh rate. Next slide, please. I'm just going fast because we need to get into the actual topic now. So the number of PMUs and where we put it would depend on various factors, and that itself is a big research area. People have worked enormously on that, optimal PMU locations with maximum observability. So you have to put PMU judicially so that you get most out of the PMU with the least cost. That's the goal. Yeah, next slide, please. Some of the PMU application, as 10 years back now, people have started coming with their own applications, but it has its own applications, like, for example, frequency monitoring, rotor angle monitoring. For example, if you have to monitor stability of the system, we typically monitor the rotor angle, right? So with the PMU data, this process becomes very easy. Otherwise, we have to run a complex transient stability algorithm to come up with a stability decision. So when PMU can directly give the angle, why don't we use it? And another important aspect is that if you already have the PMU phase angle, phase angle information from the PMU, the state estimation is no longer non-linear, it becomes linear because of the fact that you already have the phase angle information. And if you have a linear state estimation, we know that it is not iterative, that's just AX equal to B, solving AX equal to B. So that saves a lot of time. And we can also have the PMU data for modeling few components. We are going to see how do we use PMU for modeling load in this lecture, and as an example. And you can also model transmission lines, you can model generators, you can redefine a generator models based on the PMU data. Just to name a few, there are many, but I've just put up a few applications. Yeah, yes, please go to the next slide. So we will just see what are the typical differences between the PMU and the phasor data here. And you can see that the red one is the PMU data, which gives you 30 frames per second, and it clearly shows the oscillations, whereas the blue line is the SCADA data, which does not convey anything about the oscillation. This is one example where PMU, having a high refresh rate from PMU, can help us visualize the grid better. We'll go to the next slide. And if you compare the PMU and the SCADA data, you see that the PMU data, the bottom right figure shows that there are growing oscillations, whereas this is not easily seen from the SCADA data, right? One slide again. And for example, if there was an event in which you had an unstable, you had small signal oscillations, the SCADA data was kind of misleading us, whereas the PMU data is exactly saying that there is a growing oscillation. So the operator can be aware well ahead of the situations going catastrophic. He can fairly get an idea well before the event actually occurs. Whereas if you rely on the SCADA data, it does not show any oscillations. So the oscillations are not shown in the SCADA data, so which is definitely a misleading decision that we take from the SCADA. Whereas PMU gives you a lot more insight into the system operation. Next slide. Yes. So these are all some of the major motivation that Smart Grid tries to use PMU data. So I have already discussed all this points. So one major advantage is that the PMU data has the timestamp value. So it exactly says at what time the measurement was made, which is useful in making some control decisions. Next slide, please. So we all know PMU try to synchronize the data from various locations. So it uses a global reference. So whether you measure the data at Kanyakumari or at the Kashmir, it is referred to the same GPS clock. So the reference is kind of very concrete in this case. So I will not really talk about what goes into the PMU, how does it really time align and all. So, but what we need to understand is that by synchronizing the sampling process, we can have the phases measured at the same time in the phasor diagram. Otherwise, it's impossible. Next slide, please. So the phasor data concentrator processes the data package from the PMU, which has its own structure. The structure of the PMU data packets I have just shown here. It has some of the headers and the data and the check field. So sync, frame size, ID code, SOC, frac second are kind of the headers. Data 1, data 2, data n are the actual data, and the check is one tail of the data packet, which tries to ensure that things are right from the PMU. Next slide, please. So we all know that power stem is a multi time scale application. It just starts from unit commitment or system planning, which happens from years, to voltage stability or voltage excitation control, or even lightning phenomenon, which can go to microsecond time scale. So it can range from microseconds to years. The power system events, you can have dynamics ranging from microseconds to years. That's one of the very typical characteristic of the power system. So, right. So we are going to concentrate mostly on the time frame from millisecond to minutes. Will not go beyond that. So we typically use PMU data to make decision in this time frame of milliseconds to maybe say a few minutes. Next slide, please. Yeah. So this is what, again, a different way of looking at it. This is taken from the popular Sauer and Poi book on power system dynamics. The lightning propagation has the timescale of say 10 power minus 7 seconds, and the boiler dynamics is ranging from in timescale of minutes. So we need to really model a system in such a way that we exactly capture the dynamics that we want, and we do not model the system to unnecessary detail. For example, if we have to model the load frequency control, we don't have to model the lightning phenomenon, because lightning phenomenon is a very fast phenomenon as compared to load frequency control. And when we talk about lightning propagation, we don't really consider the governor or frequency control or transient stability, because the lightning is you say at least maybe 10,000 times faster than the transient stability phenomenon. Yeah, next slide. So we are going to talk about few PMU applications. One is a model validation for generator line, transmission line, SVC, STATCOM, load. So I'm going to talk about load modeling in this talk, and we're going to talk about automated control using PMU applications. So these are the two focus areas for this lecture for today. Next slide, please. Yeah. Okay. Any questions until now? Any questions? Okay. We will actually see how do we model. Okay, I got information now. Okay. So let's see how do we model loads using the PMU data. So see, we all know that we have all seen that how complex a power system can be. So it's a very complex man-made system. What we typically do when we do research in power system is that we don't actually play with the actual devices. No one is going to allow us to put your control unit on a 400 kV transmission line directly. So we rely on models, and the models are put in computer programs, and we run the computer programs to kind of simulate the dynamics of the physical device. That's what we mean by modeling. So modeling of generators, transmission lines are kind of well established. So we have well established models for generators, transmission lines, but modeling loads is still a very gray area. So this is because the load has a very diverse components in itself. But for example, the load can be anything from a tube light to an electric vehicle. So you cannot just have the same model for a tube light and for an electric vehicle, obviously, because they have their own dynamics, right? And the motivating factor is that most of the utilities do not use proper load model for their analysis. So they simply use constant power models or zip model, right? Constant impedance, constant current, and constant power models for the dynamic studies. And only a few utilities use some detailed load models for their simulations. That's one thing that we need to remember. Next slide, please. So why does this question of load modeling come on the first place is that because of some of the events that had occurred of late. So 1996 was a major event in which people learned the importance of load modeling. So this 1996 August 10 is a very well-known, very popular blackout that happened in US. The system had lost its stability and there were increased oscillations. So after the event had occurred and everything was right, people tried to do some post-mortem analysis. So they wanted to reproduce the growing oscillations through the simulations. So when they used very simple models for the load, they could not match the actual data that they recorded during the event. But when the model was changed to say an induction motor model, they could capture the actual dynamics with from the model that they were trying to develop. So this showed that wrong load model could lead to wrong analysis results. Yeah, so that's why it's very important to use load modeling. Yeah, next slide. So there are two types of modeling approaches. One is what is called as the component-based modeling approach, and other is a measurement-based approach. So in this whole lecture, we are going to talk about the measurement-based load modeling. Nevertheless, component-based load modeling has its own advantage. So in which we try to aggregate the load from very diverse load classes, and we kind of aggregate them. So one disadvantage of this is that given the number of loads is large, this exercise could be very time taking, and it could be challenging, and this is also very difficult to do. On the other side, one of the advantages is that this type of approach can give you a physical insight into the model. So this is completely a white box model, I would say. Now let's go to the next slide. So measurement based load modeling is nothing but you just get the measurements, and from the measurements we try to develop a load model. So we typically put some measuring devices such as PMUs at the places wherein we would like to model the loads, and we would try to get the load model from the measurement itself. So we continuously tune the parameters from the measurements. This enables real-time modeling of the loads also. So, but the major drawback is that unless and until you have a disturbance, you cannot do this exercise, because if nothing changes, you cannot do anything to the parameters of the load model. Next slide, please. So the way we do the measurement-based load modeling is that we have the actual load, and we measure real and reactive powers, typically P measured and Q measured, and we have a load model for the corresponding load, and we simulate the the simulated powers are PS and QS. We try to take the difference between PM, PS, and QM and QS, and we form an error function, and we run an optimization algorithms to tune the parameters such that the simulated values become close to the measured values. So at that point of time, we say that the error is minimum. So we have and the corresponding parameters are the load model parameters. This is how typically a measurement based load modeling is done. So if you see here, if there has to be some disturbance data to capture the dynamics. If nothing is there, then of course we cannot model the load. So we need a disturbance data for doing measurement based load modeling. Next slide, please. So we'll talk about some of the standard load models that people use. We use exponential based load models, and we use zip model. We are all aware of that. So in an exponential model, KPV and KQV are the parameters that we need to find out. And in case of the zip model, alpha Z, alpha I, and alpha phi, the coefficients of constant impedance, constant current, and constant power are the parameters that we would like to estimate. So these are all static load models. So the equations that relate the power and voltage and frequency, they are all algebraic functions, right? So because we are not modeling in dynamics here. We go to the next type. Next slide. And we also have dynamic load models in which we try to capture the dynamics of the load. So in this set of equations, if you could see, the degree of the differential equation is just one. So which means it models only the first order dynamics. So the parameters that we need to estimate are TP, TQ, alpha S, beta S, alpha T, and beta T. From the measurement. So this is the first dynamic load model which was proposed by Professor Hill. We'll go to the next slide. And we all know that major load, majority of the loads they consist of induction motors. Without induction motors, no load is complete. So almost every dynamical device has some sort of induction motor in it. So that's quite sensible to model the induction motor. So induction motor is modeled by its own equivalent circuit, and we model the rotor dynamics of the induction motor. And to model the static component, we use the zip model. So your total load model is now the zip model plus the induction motor model. Next slide, please. So now let's see how do we exactly use this load modeling in RTDS. So this is one system. RTDS is a real-time digital simulator that we had, which can simulate things in real time, near real time. So this is one synthetic power system that we developed in the RTDS, and we put a PMU at bus number 4. So this PMU could be a software PMU which is inside the RTDS, or it could be even hardware PMU. We used both hardware and software PMUs. And to create a disturbance, we said without disturbance, we cannot model the load in the measurement-based approach. So the transformer T2 had taps, and you could change the taps to vary your to get step changes in the voltages. Next slide, please. So this was the overall configuration. So the system was simulated in the RTDS, and you have what is called as a GTNet card in the RTDS, which gives you the 37.118 packets. And then to get a PDC, we used an open PDC that is free. That's a free firmware, and IPDC, which is developed by IIT Bombay. And we used a certain optimization algorithm to minimize the error between the measured values and the simulated values. Next slide, please. So we did this for various types of load models. The first figure on the top left is the measurements. So the actual load, so in this case, the one thing is that we know what the load is. So because it's the simulation, so we had put an induction motor in parallel with a zip load. So we see if we get the same result, while doing this load modeling exercise. But in actual practice, one should note that we don't know what is the actual load downstream of the bus at which you measure the load. So until you see the error to be 0, we keep doing the load modeling exercise. So in this case, it was easy because we knew what the load was, so we could make out some conclusions out of that. So the step change in the voltage was produced by changing the tap, and you see some of the second order dynamics, and these second order dynamics are because of the induction motor. So the first figure on the top right shows the results of the zip model. You see that the zip modeling does not model the dynamics at all, because zip model is a static model. When you come to the bottom left, you see that we model the load using the first order dynamics, and you see exactly only the first order dynamics is captured. The second order dynamics is not being captured. And the bottom right figure, you see there's a very close correlation between the measurement and the zip induction motor model, because the zip induction motor model captures the dynamics of the motors as well. Next step. So this was the case with an actual with a synthetic system. Now one step ahead, we did the same exercise when we tried to model an induction motor in the lab. So the induction motor was driven through a DC generator, and the resistive load is to capture the static part of the load, and the induction motor would be the dynamic part of the load. And you could see the PMU here. So we measured the stator voltages and stator power from the PMU, and we used this computer to record the data and to get the results. So we again tried to model this induction motor in parallel with the static resistive load, with zip model, with the recovery model, and the zip and induction motor model, and we will see how do the results look like. Let's go to the next slide. And you see that this is the top left figure shows the disturbances that we have measured. So you see that now we approximately have a step change in the voltage, and we have the corresponding response of the real power. So again, the zip model is not able to capture the dynamics of the model, whereas the recovery model, which is shown at the bottom left, tries to model only the first order dynamics, whereas the second order dynamics is left uncaptured. If you go to the bottom right figure, it models both the first order and second order dynamics, because it's an induction motor, and an induction motor and zip motor model obviously gives you better results, because the actual load that you're going to model is an induction motor there. So obviously the results would match. Next figure. So next slide. So in this case, we are going to go one step ahead, and we are going to model the entire IIT Kanpur campus load using the PMU data. In this case, the IIT Kanpur was deriving its power from a 33 kV feeder, and we have this 33 by 11 kV substation, in which we had installed the PMU on the 11 kV side, and there were CTs and PTs. And we changed the taps of this transformer to produce very small changes in voltage, because the reason is if you have very major change in voltages, people would sense it, and there could be some false alarms and all. So we did this exercise in very early in the morning, like 3 o'clock or 4 o'clock, so that people do not notice the change in the voltage levels. So the PME was put at the 11 kV side of the 33 by 11 kV transformer, and we use Ethernet to get the data into the computer, wherein we ran the modeling algorithm. Okay, next slide. Next slide, please. Okay. So again, as in this case, you will see that the top left figure shows the measurement that we made, and the top right shows the results of the zip model. The zip model is able to capture the static part very well, whereas the dynamics is not being captured by the zip model. The bottom left figure shows the first order model results. You see that only the first order dynamics is completely captured. The next figure on the bottom right is the zip and induction motor model. In this case, we have an error between the measurements and the model output, because the actual load, that is aggregated load of the IIT Kanpur campus, is not just the induction motor. It might have there could have been more other types of loads, so we could not capture those dynamics. So it was only an approximation. So but nevertheless, the zip induction motor model was able to almost match the dynamics, but not to the complete extent, because some of the dynamics could be of higher order, which is not being captured by the zip induction motor model. Yeah, next slide, please. Okay, any questions until here? Okay. So now that we have modeled the loads for balance disturbances, we just thought the balance disturbances are kind of quite uncommon, whereas the unbalanced disturbances are the most common disturbances. So we used we used a different type of modeling approach for modeling the induction motor in DQ domain. So we converted all the ABC values to DQ domain, and we tried to model the induction motor here. Let's go to the next slide. So you see that for an unbalanced disturbance, there are double frequency oscillations, because there could be negative sequence components which can have twice the frequency of the positive sequence. So that's why we have this 120 hertz oscillation. This we got it from the RTDS. So what we did is that we created an unbalanced disturbance, double line to ground fault, and we cleared it after 6 cycles. So you can clearly see that the RTDS data typically gives you the PMU values here. And you can see the double frequency oscillations that arise because of the negative sequence in the unbalanced disturbance. Next slide. So other important observation that we made here is that as the percentage of the induction motor goes high, the third order model for the induction motor. By third order, I mean you have rotor dynamics and you have the shaft dynamics. Fifth order means you include also the stator dynamics. So as the percentage of the large induction motor model goes high and high, you will see that the fifth order model has less error. Percentage error is less, whereas the third order model is less and less accurate because the error is almost 15%, whereas the error is 2.75% when you had 100% of the load as the induction motor model. So next slide. So this gave rise to another study that we made using PMU and the RTDS to see what is the data rate that we need to have when we try to obtain the data. See, because like for example, you get data at a very high rate and you don't have a storage space and you don't want that accurate dynamics, then there is no point in getting the data right. So as a recording device, a PMU or a fault recorder should have some of the important attributes, like we need to look at the important attributes like what is the maximum data rate that it can support, what is the recording interval, and what is the onboard storage, the storage that you have on the recording device itself. And the measurement data rate also depends on the type of disturbance and the nature of the load model. So now we are going to see what type of disturbance and what type of load model and how it is being affected by the data rate. Data rate means the rate at which you get the data from the sensing device. Next slide, please. Okay. So this shows that for a balanced disturbance, balanced and small disturbances, a data rate of 20 frames per second, 20 phasor per second would be good enough to get a very reasonable accuracy. And for balanced and large disturbances, we need to have 240 frames per second to achieve the same accuracy. So in case you reduce the data rate, your accuracy would go low. For unbalanced disturbances, we need to still have 240 frames per second because you have an 120 hertz phenomenon coming out because of the negative sequence that is coming because of the unbalanced disturbance. So the disturbance type also dictates the data rate that you should get from the PMU. Next slide. So for various types of load models, again, we have that, we see that for zip load model, which is static load model, a data rate of 10 frames per second would be good enough. Whereas for the recovery load model, you need typically 60 frames per second. And for the zip plus induction load model, we need a little higher data rate, say of 240 frames per second. See, this 240 frames per second means for a 60 hertz, it's going to be every quarter cycle you need to have a data, which is not possible with the current PMU, but you can get it from fault recorders. That's not a problem. So, but at that time we didn't have fault recorders, so we used the RTDS itself as a fault recorder to give the data out. So that was one advantage. Next slide, please. So to summarize, so this the whole thing on load modeling, what we saw now is that we saw that PMU data can help us in modeling various types of load model, and the amount of data that we get out of the PMU also depends on what type of load are we modeling and what type of disturbance is being created. So in places wherein there is no actual PMU, you can use the simulated data from say an OPAL-RT and RTDS as your PMU data to model the loads. That's the summary of this part of the lecture. So any questions here? Any questions? Okay. We'll go to the next slide. So we are going to now use the load modeling and PMU for designing the wide area damping controllers. So we did this with the help of the project funded by Department of Science and Technology. So yeah, okay, it's okay. You can go to the next slide. So this wide area damping controllers is to model small signal oscillations. That is one of the major threats to the power systems now. So to reduce the small signal oscillations, we use typically conventional power system stabilizers, which we call it as CPSs, which means conventional power system stabilizer. So the CPSs is affecting in damping the local modes, but for the inter-area type of load model, inter-area types of oscillations, CPSs may not be effective. So we need to use some supplementary damping controllers, which should be wide area, to damp out this inter-area oscillations. Next slide, please. So one important note that we have made using the August 1996 phenomenon is that the load models impact the inter-area oscillations to a very larger extent. So, however, changing the load models to a very complex form, we were able to match the simulations with respect to the measurements. And the load models which are dynamic are more can have better influence on damping the electromechanical modes of oscillation. So these are some of the observations that were made using the prior studies. Next slide, please. Yeah. So the type of load model that we are going to use in this study is a little bit more complex. So it's going to have a large motor, which is LM, a medium motor, which is MM, and a single phase AC motor, which is shown here, and a static part. The static part can model lighting or heating loads, and we are going to also model the feeder which comes from the transmission level to the distribution level. So we're going to model the feeder impedance as well here. So yeah, next. Okay, it's okay. We go to next slide. So so we are going to consider three load classes: residential loads, commercial, and industrial loads, and we are going to have the load components as heating, lighting, static, trip load models, and medium motors and the large motors. Trip motors are your AC motors. So we will see what is the effect of this AC motors a little later. We are also going to consider feeder impedance RF and XF. So these components of the load, heating, lighting, static load, and everything is going to be different for the three classes: industrial, commercial, and residential. So to note, residential, commercial, industrial load classes, heating load, lighting load, and trip loader modes are the load components in them. And the proportion of these components in the three classes are different, obviously, and they are different on a hot summer day and a cold winter night. For example, if you take a residential load model, you see here on the last column, the on a hot summer day, the heating load is only 10%, whereas on a cold winter night, the heating load goes up to 50%. Similarly, on a very hot summer day, we are going to see that the induction AC in the single phase motor, AC motors are going to be 50%, and whereas the other types of load models are relatively less. So on a hot summer day, the contribution of the single phase AC motor is more. So because people use more AC during hot summer days. So this is just to have two extreme cases, because we know that the load models and the load components, everything could change depending on the weather and the season and all. Next slide, please. So we have also modeled the SVC in this case. So SVC model is done. So this is from the standard literature that we took out. So so for this SVC model, we added an additional damping controller, which is shown in the bottom block diagram. So the VS is the supplementary voltage signal to damp out the interior modes of oscillation. So we use a phase lead compensator for the damping control for SVC load. Yeah, next slide. And we also had a DFIG in the system. So we added the damping controller on the rotor side controller. So the input signal is the signal that we get from the PMU, and this damping controller is added to the on the Q axis of the rotor side controller to damp out the oscillation. So we should remember that the C damp is the additional damping controller in addition to what already is there on the rotor side controller. Next slide, please. So when we design the wide area damping controller, we need to follow a few steps. Like for example, choice of the control architecture. First, we need to design what type of architecture are you going to follow, and then we are going to see what is the right wide area signal in which the oscillations are visible. And then because we're using a PMU from a geographically different location, practically there is a latency and we have to compensate for this latency. And that's why we're going to have this delay compensation. And the fourth step is to design the controller. The fifth step is to validate your design using offline simulations, using offline tools such as PSSE or DSA tools or the other types of Power World or anything like that. And then we go for real-time validation. Finally, we put it on the field implementation. So these are some of the steps that we sequentially follow and we design the wide area damping controller. Okay, next slide. So the control architecture in this case is kind of a little decentralized, in which we get the data from the PMU, from the power system using the PMU, say Y1, Y2, up to YK are the PMU data. And we pass this data through a time delay compensator, because the place where you measure the data could be geographically far from the place wherein you have the controller. So we need to have the time delay compensator module. And then you have this wide area damping controller, which provides the supplementary damping signals to say SVC or DFIG, or even to an AVR, existing AVR of the generator. So this is the control architecture. Next slide. So the way we select the signals which have to be the inputs, and the signals where the output has to go would depend on what we call it as controllability observability index. So suppose if x dot equal to x plus bu is the model for the is the state space representation of the power system, and y equal to cx is the state space representation, where a, b, c have their own usual meanings. We can apply the controllability observability indexes using this using left and right eigenvectors. I'm not going to go very deep into the mathematics of it. And the joint controllability index is the product of the controllability index and the observability index. So based on this index, we are going to select which signal would have the maximum information on the of the oscillation. For example, if there is an oscillation near say Chennai, it's kind of doesn't make sense to get a signal from Meghalaya to damp out the oscillations, right? Because you don't observe the oscillations from the signal that you get from Meghalaya for oscillations in Chennai. So that's why this index is very important. Next slide, please. And so to compensate for the delay, we use a very simple logic. We measure the time, stamp at which we measure the data, and we measure the actual time stamp. So this difference, the t GPS minus t stamp, would give the delay. So if there was no delay, TD would be 0. If there is a latency, then your data would be arriving later than what the timestamp of the GPS is shown on the data packet. So this is called time skew. Next slide, please. So once we compensate for the delay, so the delay compensation is done using Kalman filtering. So I have not listed out that here. So we model the controller using a fuzzy logic based controller because why should we go for a fuzzy logic controller? The answer is because the load model parameters could change. So in order to have the variation of the load model parameters being captured, we use TS fuzzy system, and the system stabilized by an output feedback controller, which is shown in this equation: U of t equal to I equal to 1 to R ui ki y of t, where y of t is the output measured signal. And we are going to measure the ki's as the gains, which are the controller gains for this particular type of controller. Next slide. So the next step is, once the controller is designed, we have to kind of validate on a very practical system. So we use Southern India Power Grid system and IEEE 13 system both. So I have just showed the results for the Southern India Power Grid system, which typically had around 1,300 buses, 530 generators, 800 loads, 6 HVDC lines, and 80 wind farms. So it had few eigenvalues which are critical, and for each eigenvalue we had an input signal and we have an output signal, which is determined by the controllability observability index, which I just explained. Next slide, please. And so we validated the performance of the controller using some disturbances. So we use 3-phase fault and the most critical line outage fault. The most critical line is the line that comes from Neyveli to Sriperumbudur here. So we made an outage of that line, and we could see that the conventional power system stabilizer and the local controllers, they are not able to damp out the oscillations, whereas the proposed controller is able to damp out the oscillations very fast. Even for a 3-phase fault, we could see that the other two types of controllers fail, whereas the proposed controller stabilizes the oscillations. Next slide, please. So this shows the results when we have sudden changes in the load model parameters. Suppose that you increase the on a hot summer day, suppose the amount of AC load becomes very high, you see that the other two types of controllers, the conventional power system stabilizer and the local controllers, they are not able to damp out the oscillations, whereas the proposed controller is able to damp out the oscillations. Steady state is being reached. And the bottom figure shows the design of the controller with the uncertainties being accounted for, and without the uncertainties being accounted for, uncertainties of the load model. So you see that when you design the controller by considering the uncertainties, the system is getting stabilized. So this is also one important observation that we have made. Next slide, please. So then we wanted to do this thing in real time. So what we have done is we have simulated this on real-time system using RTDS. So we had an hardware which was quite enough to simulate only 13 bus system. So we modeled the 13 bus system in the RTDS, and we got the data from both hardware and software PMUs. So in this case, we don't really have any delay because we are measuring the data from the simulation. So what we have done is that we have delayed the signal intentionally, and then again we have compensated, and then we have designed this controller to damp out the oscillations, and this control signal is fed back to the RTDS simulation through the output feedback kind of stuff. And we observe 3 critical eigenvalues, and for these 3 critical eigenvalues, we have selected what should be the right input signal and what should be the right output signal. Next slide, please. So the first figure on the top bottom on the top left shows the original signal that we have measured and the delayed signal. The original signal is shown in a dotted line and the delayed signal is shown in the red line, and the compensated signal is shown in the blue line. So the delayed signal is being compensated. So after the compensation, the compensated signal and the measured signal, they become almost equal, because we have done the time domain compensation here. And in real time, we actually we simulated a loss of load condition in bus number 21 in IIT bus system, and you see that the proposed controller damps out the oscillations very quickly, the blue solid line, whereas the without time domain the time delay compensation, the oscillations are not being damped out very quickly. So which shows it is really very essential to compensate for the time delay. On the bottom left, you see that with the load models being uncertainties being considered, you see that the oscillations are sustained, and when you consider the load models, the controller damps out the oscillations very quickly. So this is to show that the load model uncertainty has to be considered. And the final figure on the bottom right shows the performance for a three-phase fault. For a three-phase fault, you see that the proposed controller again damps out the oscillations very quickly, whereas the conventional power system, which is the black dotted line, it shows that the system fails. So you cannot stabilize the system using the conventional power system stabilizer. Next, okay. So in this, we have seen how do we use the PMU, and we have considered some of the practical aspects of time delay for designing a wide area damping controller to damp out the oscillations, to damp out the inter-area modes of oscillations in the power system. So this is the second module of the lecture. So I think I'm on time. Any more questions on this? Okay, we'll go to the next slide. So in this, we are going to come up with a cyber physical testbed for distributed monitoring and control. So again, this was done at Washington State University, Pullman. So the credit goes to them again. So we'll go to the next slide. So the conventional power system is now being replaced by traditional. The traditional power systems are being replaced by more and more distributed energy resources, and we are going to have electric vehicles. We are going to see increased penetration of distributed energy resources like rooftop PVs in the system. So this makes a way to develop controllers which are kind of decentralized in nature. Okay, let's go to the next slide. Okay, I'll come back to this slide a little later. We'll go to the next slide. Okay, now I think I'll define what a resilience is. So the resilience is nothing but the ability of the system to come back to the original form or position after being subjected to a very large disturbance. For example, if you have a tsunami, or which comes very rare, but the effect is more, and your system is able to cope up, then you say that the system is resilient to the disturbance. We don't say the system is resilient to a three-phase fault, because three-phase fault is a more common phenomenon, but the effect is less. Whereas events like natural disasters or cyber attacks, they could be more and more, they could have more impact, but they are less frequent. So the ability of the system to come back to the original state after being subjected to such disturbances is what is defined as resilience. Next slide, please. Yeah, I think I showed that. So we can enable resiliency in the transmission systems in various ways. Like you could have a redundant transmission line or a standby control center. So that is definitely more resilient, but it is less cost effective because you have to have one more spare part. And then we can use incoming data to monitor the health of the system prognostically. Like for example, even without an event, you can just keep monitoring the health of the system, and once you feel that the system is getting worn out, you can replace the system. So that is what I mean by prognostic health management. And the other major type is wide area PMU based incoming data based protection schemes, which make use of PMU data to take corrective actions in case of an event that occurs in the system. Next slide, please. So a closed loop system typically kind of looks like this. It has the plant as the power system. So we get the data from the data sensors like PMU, and there is a communication network, and the communication network delivers the data to a control center, and this control center makes the control decisions, and the data is sent back to the communication network through the same communication network, and there is an actuator which actuates. For example, this could be a breaker or a controller, and it could send back the control signal to the power system. Thereby, you close the loop. So examples of actuators could be relays or motors. Example of sensors could be PMUs, what we just saw, weather sensors, digital fault recorders, and all. The network could be modeled. It could be a local area network or a VPN or a wide area network. So anything of that sort. And the control center is the framework in which you make all the necessary computational control algorithms in the control center. Next figure. So you have typically three control architectures, like centralized one, which is shown on the left. So in which every every node communicates to a single node, and that single node makes the control decisions. So the disadvantage is that if this central node fails, everything would fail. So this is most less resilient. It's the least resilient case. And you come to the middle of the figure, it shows the decentralized case in which a group of nodes communicate to other group of nodes through a leader node. The leader nodes communicate among each other, whereas the slave nodes communicate only to the leader node. So this is little bit more resilient, because even if one of the leader fails, the other leader can take up the computation and it can do the work. The third type is the distributed type of control, in which every node is a computing node, and this involves the most complex computation architecture. So we are going to not deal with this now. We will take this decentralized approach, which is shown in the middle of the figure, and we will take a use case to demonstrate the effectiveness of the decentralized control now. Next figure. So why do we need this distributed monitoring and control? Is that it's because the power grid is becoming more and more complex, and because you're going to have more and more distributed energy resources. So a centralized system could be non-scalable, it could be slow. The local controllers for such systems could be, it need to be hard-coded, and they are not fault-tolerant. So the distributed system is relatively more resilient, it is scalable, it is fast, and it is robust to any type of disturbances. So and hence we need to come up with a test bed. So when I say that there is a distributed control mechanism taking place, we need to come up with a proper test bed which can simulate the cyber physical nature of this distributed control, and we were exactly going to see what this controller is in coming slides. Let's go to the next slide. So one cyber physical testbed we are going to talk about. Yes, okay, there is a question. Yeah, someone raise the hand.
Shiva Prakash, do you have any questions? Sir, please continue, sir.
Okay. So one thing that we have to clearly notice, the smart grid is a typical cyber physical system. So we have to model the cyber system, you have to model the physical system, and the most important aspect is we model the interdependency between the physical and the cyber system. That's the whole idea. So let's go to the next slide. So and the cyber physical testbed comes out with its own challenges, because now because we may have to incorporate more and more attributes to it. For example, we have to elect a leader among the given set of nodes. We have to discover the loss of the leader. We have to form the groups dynamically, and the other type of thing is that when you develop a cyber physical testbed, you have a variety of devices and they have their own protocols, and you have to kind of interoperate these protocols on these hardwares to develop a complete test bed. So simulators, PMUs, DFRs, relays, and controllers are such devices which are typically present in the test bed. Next slide. Okay. So some of the protocols that we have handled is C37.118 PMU data PME protocol, and DNP3 for weather sensors, IEC 61850 for substation automation, and TCP for the intra-group communications, the communication between the group and among the groups, and Modbus for actuators and relays. So these are some of the protocols that we have handled in developing this particular cyber physical testbed. Next slide, please. So when we design the testbed, we have to have few we have to go few steps. We have to identify what are our specific application requirements, and accordingly we identify suitable hardware and software, and we try to understand what are the protocols that are involved, and we deploy the applications. So then we test the algorithm for various cyber physical failures, both cyber and physical failures, and then we validate our results using offline simulations. So this is how we typically come up with a testbed design and validation aspects. Next slide, please. Okay. So the power system, to model the power system itself, we have used both RTDS and OpenRT to simulate the system in real time. So for the sensors, we have made use of phasor measurement units, and for distributed controllers, we have made use of fog routers and beagle bones. And for the actuators, we have used relays and controllers. So yeah, you can just press the next button. Okay. So these are all the hardware aspects of it. Let me just go to the next slide. I'm not going to talk about Cisco fog routers because we'll just understand that these are kind of a mini computers in which we can deploy the applications itself. Next slide. And the software requirements, as I said, is that it is not only necessary that we have the hardware for the testbed, we also need to have a software which can incorporate all these attributes that we have really require, like failure recovery, resiliency, discovery, group formations, and all. So we have to have a software module which can take care of such cyber physical aspects of the testbed, and we are going to see one such software which we have made open source out of our research. Let's go to the next slide. So this is called REAPT's Resilient Information Architecture for Power System. So it has multiple layers. The most bottom layer plays with the hardware. It has interfaces with the sensors, actuators, and all. The middle framework, the middleware is the place wherein we have incorporated all the necessary attributes of a distribution control. And the topmost layer is the place where we have remedial action scheme, microgrid management, state estimation, data analytics. You can have any application. So in this case, I'm going to consider remedial action scheme as one typical applications on that. Next slide. So we have taken IEEE 14 bus system as an example. IEEE 30 bus system as an example, and we have put this typical controllers on the system. Maybe you can control enter. And we have developed the own communication network using NS3 simulator in the power system. Next slide. So with all this substations, sensors, computational units, we are going to come up with an application wherein we are going to demonstrate this distributed control aspect of the cyber physical smart grid. Next slide, please. I'm just skipping. So I'm just coming to the application. So once we developed such a platform, the application was that we were supposed to cut excess of wind, because in one area in Europe there was excess of wind and we need to curtail the wind, otherwise it was overloading the transmission lines. So the requirement was that we optimally curtail the wind so as to control the power flow on the feeders on the transmission lines. Next slide. So for this, we're going to develop a resilient, a remedial action scheme for the optimal wind curtailment. So the existing architectures were all not scalable, so they were all centralized in nature. Whereas the one that we are going to develop is going to be decentralized. The disadvantage with the centralized node is that even if the centralized node fails, everything is going to fail. And when with the distributed node, though one of the nodes fails, other nodes will try to still perform, and it will not completely paralyze the system. Next slide, please. So we are going to use the dynamic RAS, dynamic remedial action scheme. So this is going to be measurement based, and it is going to be fast, and we are going to rely on the PMU data for the measurement. Next slide, please. Okay, so so I'll better play a video so that which can, in interest of the time, I can. So can you? I'll share this folder with you. Can you please play the video for me? So I'll give you the access. So what should be the email ID to which I should give you the access?
Sir, is it possible to play your video from your laptop?
No, the problem is then the screen sharing would be affected. I'm not able to share the screen. It is showing some error. I'll share it on a Google Drive. You can just play it from there.
Yes, sir, please.
So what is the email ID that I should give?
SGDCO.
SC
SGDCO.
SGDCO
At
okay,
sastra.ac.
@sastra.ac.in. Okay, I've shared the Google link. You can actually play the video. Just let me know once you have got the video. Once you have got the folder access. So yeah. One thing is that you have to take out the headphones so that everyone can listen. If there is headphone there, the audio would also be audible to rest of the people. So have you received the invite? Hello. Yeah, you can play this demo video on ARPA even. Yeah. Oh, I think the audio is not coming. You can take out the headphones if there is headphones connected there.
No, sir, we have not connected any headphones.
Okay. Okay, so I'll only explain. So the remedial action scheme that we have designed is going to curtail the optimal amount of wind, and the constraint is that we are going to utilize the line capacity to the maximum limits. So this is the mathematical formulation of that, where we are going to maximize the wind and we are going to minimize the curtailment. So this is the example of the 14 bus system. So we have increased the amount of wind, and you see that this particular line gets overloaded, which is shown as the red color. So once the application detects an overload, it tries to curtail the wind. So it comes back to the nominal values. So this is the test bed that you can see here. This is the RTDS, and for each substation we have put a similar arrangement. So you can see the markings, PMUs, actuator, and the complete setup here. Yeah. Beagle bones are the bones in which beagle bones are the places in which we put the computational algorithm. We divide the entire power system into groups and we try to minimize the curtailments. So here we are going to perform certain tests. So the normal operation, we're going to increase the wind, and you will see that you see that yellow line is going above the line limit. So the algorithm gets triggered, it senses an overload. So there is it turns red, and then this is the overload is getting detected here, and the algorithm kinds of brings back the line limits to the nominal values by curtailing the amount of wind. Now system returns to the normal operation condition. So in the next case, we are going to remove one of the computational blocks so that to see if the other two blocks function properly. So we shut down the first node, and now on we increase the wind power, and that overloads the transmission lines. So one of the node is out, and there is an increase in the wind power, and there is a line overload which is detected, and the rest of the other two nodes detect the failure, and they take out the operation of the node that was shut down, and the system still comes back to the normal scenario. So the next case would be in which we did remove the communication line. We make a communication failure between the nodes, and then we see what is the effect on that, and that is shown here. And I'm going to plug off the communication link for one of the nodes. So there are 3 nodes here. So the power system is divided into 3 nodes. I'm going to switch off the power supply to one of the nodes and remove its communication link. And what you can see here is the system is going to detect this failure. System was shut down, and the other 2 nodes have detected the failure of the node 1, and they now start the function of the malfunction node. They take up that burden and they detect the overload of the transmission because of the amount of wind increase. They curtail the wind, and the system comes back to the normal operation scenario. So the line overload is detected and everything is brought back to the normal operating conditions. Okay. Okay, I think I will now stop here. You can come back to the presentation. Any questions on this? Any questions? Can go to the. Thank you. I'll stop my my lecture at this point. The takeaway point is that the distributed control or the decentralized control is more resilient to single point failures. Even though the system performance might be deteriorated because of a single node failure, the entire system does not collapse. That's still up and running. That is one of the important advantages of decentralizing things, and we have shown that using an use case like, for example, the wind curtailment remedial action scheme. Okay, I'll stop my presentation here. If you have any questions, I'll take them.
Participants, if you have any query or doubt, you can ask to Dr. Vignesh sir right now.
I'll share the presentation and the link for the REAPS platform to use, so that if you want to work on this distributed application, you can start thinking about it and you can work on that.
Sure, sure. Thank you. Please feel free to type your questions in the chat box. Okay, sir. I think no
more
questions
questions
from the audience.
Okay.
Can wind off the session, sir.
Yeah. Thank you so much.
Thank you so much, sir.
I would like to thank the management, electrical department, and organizers, and of course Dr. Narayan for this opportunity. Thank you very much. You can contact me through email if you want any support from my side. Yeah. Thank you.
Thank you, sir. Thank you for your wonderful presentation, and also thank you for accepting our invitation.
Yeah, thank you. It was my pleasure.
Thank you, sir. Thank you.